between jobs. Okay, so that is a question that, that is what part A is asking. So how are we going to think about this? So remember that you're trying to translate words into math. So in this particular case, I'd like to think about, this guy as an X, right? So I'm going to introduce a random variable. Let's refer to it as X. And X would be simply the time between jobs. Okay, so if you think about what X is, it's really modeling the time between some events, right? So this is really what we are looking at is time between events, right? Jobs are events, and this is the time between events. And we just mentioned that the exponential can be a potential model for modeling time between rare events. So here we are really assuming that, the jobs, the occurrence of jobs is rare. So therefore, if I can model X as exponential, so it might be an appropriate model here, or we can assume that with some lambda that we are going to talk about in a minute, then the question is simply asking what is the expected value of X, right? So any questions so far? Now let's go back to the definition of lambda in the exponential. So can someone tell me what was the definition of lambda in the exponential? So here I decided that, exponential would be an appropriate model to model time between jobs. Remember that an exponential is a single parameter model, meaning that lambda has to be provided for you, or you have to figure out what lambda is. So what was the definition of lambda in the exponential? So you can go back to the slides and look it up. What was lambda by definition?
Number of events per time unit.
Exactly, number of events per time unit. So we are looking then, in the context of this example, what are the number of jobs per unit time? Per minute, per second, per hour, etc. Was that provided to us?
Yes, it's 3, I guess.
Exactly, it's 3, right? We have 3 jobs per hour. That is the rate. And therefore, we are going to assume lambda here is going to be 3. Okay, great. So at this point, once you have a model for X, then you should be able to answer any probability question or any expectation or variance. Now that we know that X is exponential, the question now you can go back, to your study guide or to the slides, and we already proved or looked into what was the expected value of an exponential. So an expected value of an exponential was 1 over lambda. If you know lambda to be 3, then the expected value of X is going to be 1 over 3, just 1 over 3. I guess hour, right? That's the expected value of time. X is time, so what you get is on average, you're going to see 1/3 of an hour. Basically, that translates into 20 minutes. Questions? Any questions? All right, let's look into part B then. What is the probability that the next job, what is the probability that the next job is sent within 5 minutes? So I'm going to give you a moment to think about how you want to translate that into mathematics in terms of X that we introduced, and how do you want to write that? So I'll give you like a moment, and then I'll be looking for volunteers. So this is what we are asking: the probability that the next job is sent within 5 minutes.
Professor.
Mm-hmm.
Is this really just asking, like, how does 5 minutes compare to 1/3 of an hour?
No.
Okay.
To what?
1/3 of an hour.
No, it's asking for a probability, right? So no. Anyone? So how do you want to write this? It's a probability, right? So I'm going to write P, but it's a probability of what?
That x is less than or equal to 5.
Okay. So he said X is less than or equal to 5. So I'm just going to say the time, right, between jobs is actually less than or equal to 5. I'm just going to write that real quick. So Jimmy, you have a question?
Wait, since the time is an hour,
Exactly. That's the
I
issue.
don't think it should be 1, but like kind of like a fraction, so 5/60, something like that.
Okay, so 5 is in minutes, right? So the thinking is correct. It's just you want to pay attention to the fact that X is actually in hours, right? How do I know that? Is because the rate is given to be 3 jobs per hour. So the unit time that we are thinking of is really in hours. So you're going to have to convert the 5 into hours, right? If you are talking about X, you need to convert the 5 in hours. Is that clear? And how do you want to do that? What should you do to convert 5 in hours? 5 minutes into hours, what do you need to do? What is 5 minutes in hours?
I would make
Divide.
Divide
5
by what?
divided by 60.
Just divide by 60, right?
Well-
So the question becomes this now. So now this becomes hours. Does that make sense to everyone? So you wanted to pay attention here. You definitely have to convert the 5 into hours. Why? Because the rate is given in hours. That is the time. That is the unit time that you're considering, right? So X will be the time in hours between jobs, right? So the time in hours, I should say. So you want to pay attention to that. All right. So that becomes then the probability that X is less than or equal to 1/12, right? And how do I figure this out? Real quick. What do you want to do? What is this? What is the probability that X is less than or equal to something? That has like a famous name in probability. What do we refer to it as?
The CDF.
A CDF, very good. So we already know it is a CDF of the exponential. Well, the CDF of the exponential was given by 1 plus e to the minus lambda x, right? So what you do is simply plug in, sorry, this was a minus, I believe. So what you do is you simply plug in your lambda. In my particular case, lambda is what? Is 3, right? That is given. And then your x is just 1/12, which is this guy. So it's 1/12, this being multiplied, right? And where did I get this from? We already derived this on Tuesday's class, okay? So you just simply plug it into the formula for the CDF. So then this becomes 1 minus e to the minus 1/4, and then you can use your calculator to figure out what the probability is. Questions? Any questions? Okay, so now switching to the slides. So now we are moving on to the next distribution, which is the gamma distribution. So you should be thinking of the gamma distribution as a generalization of the exponential, which means that for specific parameters of the gamma, it boils down to the exponential. But if you change your parameters, then it becomes something that is different than the exponential. So what is it used for? Remember that the exponential was used to model time or time between rare events. So now let's talk about what can the gamma distribution be used for. So you wanted to use it. This is key with the exponential. So if you have a certain procedure consisting of alpha independent steps, so you can think of this as some sort of like a you know, a processing a sequence of, you know, processing something, and it's done in sequences. So you're looking here at alpha independent steps, right? So here's, you're having step 1, step 2. So you're thinking of a process with alpha independent steps. Here's step 1, here's step 2, and here's the alpha step. And each step takes exponential lambda amount of time. So in order for the first process to be completed, I'm going to call the time of that to be x1. I'm going to call x2 to be the time of the second process to be completed. And I am going to call the last, or the time for the alpha process to be completed, x sub alpha. And what I'm essentially interested in is the total time that it takes for the process to be completed in full. Now, in order for the process to be completed in full, you need to complete step 1, step 2, up to the alpha step, right? And I'm interested in the total time. What we do know is that the time for each process is actually exponential. Remember, we just talked about the exponential. It's a nice model to model time. So the time for the first process to be completed, I'm going to think of it as exponential. So I'm going to go exponential of lambda. And the time for the second process to be completed, we're also going to think of it as exponential lambda. And the time for the alpha process to be completed, we are going to also think of it as an exponential lambda. So so that is kind of what the model looks like. The final total time of t can be modeled as gamma. So if you have this particular setup, so t can be modeled as gamma. Now you can see that I have two things going on. I need to know how many steps I have, right, for this full process to be fully completed. And in this particular case, I have alpha steps. So you're going to need to know the alpha. And also you're going to need to know what is the lambda, or what is the rate of the exponential, right? So you can see that, the assumption here is that every particular x, or the time for each process, is modeled as the same exponential with, the same parameter lambda. So here we're not assuming that lambda changes. Lambda is actually fixed across the independent steps. So you're going to have to tell me how many steps I have and what is the rate for each step, which is lambda. So it's a 2-parameter distribution. Now, the gamma distribution is often, so generally, again, we use it to model the total time. All right. Now, why did I say that this is a generalization of the exponential? Well, if you happen to have, lambda to be 1, meaning that I only have one step to this process, then this boils down to just an exponential. You're looking at x1, which is basically the total time, right? Because you're assuming that the full process only needs one step to be completed. But the time for the first process, for the first step to be completed is exponential, right? And you just have one step. So when alpha is 1, your gamma simply becomes the exponential in this particular case. So any questions on what is a gamma distribution? It's really important to understand what it represents, so that when you are presented with a problem, you can figure out what's the appropriate model for it. Okay. Now, it turns out that, because the gamma is a 2-parameter model, you can give me an alpha and you can give me a lambda. There are infinitely many lambda, combinations of alpha and lambda values that you can, assume for the gamma. And that is going to affect the shape of the distribution. So you have infinitely many shapes, and it's so versatile that the distribution can be concave down, can look something like this, concave up, basically. So it's versatile, and it takes many shapes, just because the alpha and the lambda can be really You know, you have infinitely many choices of those. Okay, so in terms of how we write this, we say that gamma is gamma of alpha and lambda. Now, what is the PDF? Now, the PDF is going to be given by this function when x is positive. Now, why x is positive? Because we are modeling total time, and the time has to be positive. So this is a distribution that it's always, you know, that's only defined when for x, for positive x. Now, the alpha and the lambda are basically called the shape parameter and the frequency parameter respectively, right? So when you're using computer softwares, generally we refer to the alpha. So you're going to need to provide it with an alpha. So they call it the shape. What is the shape? That would be your alpha. Your frequency parameter is always lambda. Okay. Now let's go back to why the PDF looks like this, or let's try to think of what this is. So the PDF, right, is given to be lambda to the power of alpha. Now remember, alpha and lambda are both provided for you, right? These are the two parameters of the gamma, divided by this gamma of alpha. So gamma of alpha is a function that I'm going to talk about in a minute, and this function is referred to as the gamma function. All right, and then it's x to the power alpha minus 1. Okay, that's fine. E to the minus lambda x. And this, again, looks exactly like what you have seen with the exponential. Now, again, x is greater than 0. So where is this gamma function coming from? So maybe I should move to the next slide. So a gamma function is a popular function in math, and this is what it looks like. So so it is defined for the domain of this function is positive. And what it is, it's simply this integral. So this turns out to be, you know, one of the important integrals in math. I'm not going to go over, you know, what is the value of, or how you actually go about integrating this. But it turns out that, so if I, let me see if I can actually copy this thing, because I need to show you what the idea is. I don't think I have space, or do I have space here? Or let's try to do it here. So if you happen to know the right-hand side, which is basically, you know, some constant that we are just going to call it gamma of alpha. I want to make a PDF out of this. So what do you want to do? Well, what you do is you simply divide both sides by 1. By gamma of alpha. Why do I want to do that? So I get an integral of 1. Right? So, so it turns out that, and that's why, so if you look at this picture, right, this is basically, so, right, so this is basically your gamma PDF. If you were to integrate this, that's going to give you a 1. So the gamma PDF is alpha lambda to the power alpha, you can see that, but then it's divided by gamma of alpha, right? And then x to the power alpha minus 1 e to the minus lambda x. So this is just a direct, derivation from the gamma function. So I know a gamma function, right? If you integrate the gamma function, it's just this integral. So the result of this integral is whatever this number is. We just refer to it. This is a symbol, gamma of alpha. And if I want to make this into a PDF, I want to make sure the integral goes to 1. So what you do is you divide both sides by this constant, and that guarantees that the integral is 1. And therefore, you can say, well, this is just some PDF that we refer to it as the gamma PDF for the gamma function. So any questions on that? So that's kind of like the story of the gamma. So it's really coming from the gamma function. Now, it turns out that if you plug in alpha if you plug in 1 for alpha, then what happens? This becomes a 1. And then this becomes to the power 0. And then you end up with the integral of the exponential, right? You're going to have lambda e to the minus lambda x dx, but now you're integrating from 0 to infinity. You do know that the exponential is a PDF, so that integral has to be 1. And that tells you that the gamma of 1 is 1. So that's the proof of why that is. Now, you can also show that the gamma of alpha plus 1 is actually alpha gamma of alpha. And that is true for any positive alpha. You know, the proof of this will be used, you need to use integration by parts, but it's doable. You can do that. So this becomes an important fact because if you have n to be positive, right? So let's say I am interested in gamma of 3. Sorry, gamma of 4. Then what this is saying is that, you know, gamma of 4, which is basically alpha plus 1 on the left-hand side, is 3, right? Gamma of 3. All right, and then what is gamma of 3? Well, gamma of 3 is going to be 2 gamma of 2, right? According to that formula, but also I have a 3 outside. Now, what is gamma of 2? Gamma of 2 would be gamma of 1 times gamma of 0. And gamma of 0 is not defined, so it'll just stop there. But what is gamma of 1? We already know that gamma of 1 is 1. So it becomes 1 times 2 times 3. So gamma of 4 becomes 3 times 2 times 1, which is basically 3 factorial. So when you have a positive integer, gamma of that integer is going to be n minus 1 factorial. All right. So this is basically discussing the properties of the gamma function. The gamma distribution is a direct, consequence of the gamma function by simply dividing both sides by whatever that constant is. And that's how we produce the gamma PDF. All right. Now, what is the variance and what is the expectation of the gamma? Well, it turns out that the expectation of the gamma is alpha over lambda. So you want to sort out who is alpha and who is lambda because this is important. You can't look at the reciprocal of that. And the variance is alpha over lambda squared. All right. It looks complicated. It's not what you want it to do. So maybe you should look into examples on how we actually would want to apply this. Any questions on the gamma distribution? Okay. All right, so I'm going to give you a moment to read the following example. I'm going to try to copy it to the whiteboard while you guys read it, and then we can go over it together. Didn't work. The thing is not copying for some reason now. I don't know why. Let's see, let's try one more time. Looks like nothing is working properly today. Okay, so switching to the whiteboard. So let's go over this problem. Okay, let's see. So you have users visit a certain internet site at an average rate of 12 hits per minute. Okay, so I'm going to write that out. So the average rate of 12 hits per minute. So 12, so this is some sort of like a rate. So 12 hits per minute. Every sixth visitor receives some sort of like promotion that comes with a form of a flashing banner. So you have every sixth visitor, would receive a promotion that comes into a form. Okay, so just keep that in mind. The question is model the time between consecutive promotions. All right, so you can try to, write a picture or try to draw a picture for this. So what do we have here? You have, users are visiting sites, right? And we are looking at, let's see, a certain internet site. So we have a particular internet site, and there is an average rate of 12 hits per minute. So you have a particular site, right? And the time, or you can think of the time as, let me think about this. Okay, so the time it takes for the visitor to get that site to get to this site is going to be X1. So here is like the first visitor, and then the time for the second visitor to hit the same site is going to be X2. Time for the third visitor to be hitting the same site, so this is a particular site, is X3. And this goes on until the sixth one. So you have 1, 2, 3, 4, and then 5, and then 6, right? So, the sixth visitor is going to get some sort of like a promotion, right? That's what it says. Now, the rate at which the site gets hit is 12 hits per minute. So I can think of the time to be exponential with a lambda of 12 per minute, right? So also X2, which is the time that it takes, is going to be a lambda of 12. And then the same thing with X3. So they all have the same exponential of the same lambda. All right. So what is the question here? So the question is model the time between consecutive promotions. So the time between consecutive promotion is what? So by looking at this picture, what do you think the time is? Right, I just wrote it down, right? These are the time. What is the time between consecutive promotion? So here's the first promotion, right? And then in order to get the second promotion, you're going to need 6 additional visitors, right? To get the second one. So you're going to have 6 different visitors again. So 1, 2, 3, 4, 5, and 6, right? Now, what is the total time can be modeled? You can see that, this is a process, and how many, segments I have, or how many steps. I have 6 steps. So I can think of this as my alpha. My lambda is already given to be 12, right? So the total time, which is basically, X1 plus X2 all the way to X6, can be modeled as gamma of alpha equals to 6 and lambda equals to 12. Does this make sense to everyone? Yes, no, maybe?
Yeah, that makes sense.
Okay, so I guess the question here is just asking to model the time between consecutive promotions, and basically what you're looking as is simply to model T. All right, any questions on this? Okay.
Is there more to the problem?
No, the question is just really modeling the time. So if I ask you then
Oh.
maybe a follow-up question, let's say find the expected value of the time between consecutive promotions, then what would that be? So let's maybe ask a follow-up question here. What would be the time, what would be the expected time between consecutive promotions? What do you guys think? Right, the time is a gamma of alpha with a 6 and lambda of 12, correct? So we already established the model. So my next question, so let's make, I can, write, build many questions, that's related to this experiment. So the question, I guess, what is the expected time between consecutive promotions? What do you guys think? What are we looking for? The expected value of what? What is the time between consecutive promotions from this picture? What is it? Right, here's promotion 1. Here's the second promotion. What is the time? This is the time, right? This is the time. What is the model of that time? What is this? What is this? What is the total? X1 through X6. What is that?
Well,
6 minutes.
That's, oh. So we actually do not know the time it takes for a customer to hit that site. We just call it X1, okay? And X2 and X3, etc. So this would be the time it takes for the first, person to actually hit that site. This would be, the time for, the second person to hit the same site. This would be the time. So the time is a variable. We actually do not know what the time is. But I can think of the total time as T. So if each one is a variable, that means the total time is also a variable. And that can be modeled as a gamma, right? So we are looking for the expected time between consecutive promotions. So if this is T, this is also going to be T because this picture is exactly the same as this one, right? So the time between consecutive promotion is just really the expected value of T, right? If you have already established a model for T, we do know, which is a gamma, we do know what's the expected value of gamma. Well, the expected value of gamma is just 6 over 12. It's just alpha over lambda. It's just 6 over 12 or 1/2, right? And then I can ask you the follow-up question, what is the variability in time between consecutive promotions? Really, my question is, what is the variance of T? Well, I do know, if I have already established that T is a gamma, I do know what's the variability in the gamma distribution. It's just alpha over lambda squared, which is going to be 6 over 12 to the power 2. So I can ask different questions about this problem, right? I can also ask a probability question. What's the probability that T is between, 2 different points that I happen to be interested in? And you just find out using either your calculator or some software, what is that probability? So I think there is another example that I'd like to go over in terms of the gamma, and I think that would ask you probability question. Great, so here we go. Okay, so again, I'll give you a moment to read the following. So any questions on the previous example? I'm sorry, I moved too quickly. Any questions on this? So always think about the picture of the gamma. This is important. That's critical. This picture, where is it? This picture, right? Gamma is always the total amount of time, right? Of X1, X2, all the way to X sub alpha. And you're thinking of each X as, the time for a particular process, and that time is a variable, right? It varies. You actually don't know what it is. So, but the t, which is the total of all of these variables, ends up also to be a random variable, right? Because it's a sum of random variables. All right, so moving on to the next example. All right, so give you a moment to read this. And while I'll try to copy it. All right, back to the whiteboard. Okay, so what we have here is that the compilation of a computer program consists of 3 blocks. Let's change to red here. That are processed sequentially, one after another. Okay, so we have 3 blocks, right? This is a computer program, consists of 3 blocks that needs to be processed sequentially. So maybe you guys think of it the other way. So here's the first block, here's the second block, and here is the third one. Okay, so one after another, each block takes exponential time with mean of 5 minutes. So the time for the first block to be compiled is, I'm going to refer to it as x1, and it says that x1 is exponential. So x1 is actually exponential with mean of 5 minutes. What would be the lambda of this exponential? If the mean is 5, right? Is that your lambda, or lambda is something else? So the time is exponential with mean of lambda. So the average of the exponential time is 5 minutes. Is that your lambda? That's my question. So I'd like to figure out what is lambda here, right? So anytime I say exponential, I need to figure out what is lambda. So what do you guys think? What is lambda? Well, I fix this box.
1/5.
1/5, very good. Right? Should be 1/5. Why? Because I said the mean, and the mean of exponential is 1/lambda. And if you solve for lambda, then your lambda is just 1/5. Okay, and your second block, the compilation time for the second block is x2. Do I actually exactly know what's the compilation time? No. I mean, one time it takes 1 minute point something, another time it takes maybe less, right? It's a random variable. And again, this random variable is going to be modeled in the same exact way. It's exponential of 1/5, or it says each block, right? That's key. So each block is exponential. X3 is also exponential with lambda of the same lambda. Okay, great. So part A, so any questions on this so far? So in part A, it's asking to compute the expectation, right? So we are looking for the E and the variance of the total compilation time. Now, what is the total compilation time? It's x1 plus x2 plus x3. It's all of this, t, which I can refer to it as t. So your t is x1 plus x2 plus x3. Each one is a random variable, implies that t is a random variable. So you guys tell me, how should I, model t? What is the best model? I just wrote it down. What is the best model for t? It's the total time, right? The total amount of time. Each time is exponential. That can be modeled as what?
Gamma distribution.
Gamma, right? Gamma is a 2-parameter distribution. I need to know it as lambda. And I also need to know what is alpha. Lambda, we already know that. That's just 1/5 because each time is exponential of 1/5. How about alpha? What is alpha in this case? Remember that alpha represents the number of steps or the number of blocks. So how many blocks do I have here?
3.
3, exactly. Right? Is everyone happy with this? So you have to establish the model first before answering any question. So part A of the question is really just asking what is the expected value and the variance of t. So what's the expected value of t? And what is the variance of t? Well, the expected value of t is just alpha over lambda. So it's just going to be 3 over 1 over 5, which is 15. And then the variance of t is going to be alpha over lambda squared. So it's just alpha over 1/5 to the power 2. So it's 25 times 3, which is going to be 75. And of course, all of these are in minutes. So the expectation is 15 minutes. The variability is 75 minutes squared because we are looking at the variance. Questions? Any questions? All right. So part B is compute the probability for the entire program to be compiled in less than 12 minutes. Also, you want to pay attention to the units. If I'm talking about if the model is defined in minutes, then we are good. If it's defined in hours or something like that, you definitely have to make the conversion, right, into the units of the model. So here the models are in minutes, so that's not a problem. So what is B asking? So it's the probability for the entire program to be compiled in less than 12 minutes. I'd like to write this, mathematically. What do you want me to write?
Probability that t is less than 12.
Exactly. Thanks, Brandon. So it's the probability that t is less than 12, right? That's what the question is asking. This is part B. All right. Once you know that t is a gamma, right? You're looking at the CDF of the gamma of this particular gamma. So I don't believe that you have a CDF for the gamma distribution on your calculator. And let me just double check that. You can also check from your end just in case I miss it. No, so I don't see it from my end. So what you're going to have to do is use a statistical software. And generally, what I use is R. I think I mentioned this a little bit in the past. So the code for this is to, so the R code is to go P of gamma. So P stands for probability. So I'd like to know the probability under the gamma distribution of 12. Now, why it's 12? So I'll get back to that in a moment, right? So we're looking at the area to the left. So P of gamma is really the is the function that gives you the CDF for a gamma, or the area to the left of a gamma distribution by default. So the area to the left of a gamma distribution. Okay. And you're going to have to give it an alpha. Now, how you're going to provide the alpha information, you're going to say shape parameter is going to be, in this particular case, 3. And then how you give it the lambda, well, the lambda is what we refer to as the rate, right? So that's just going to be the rate of, which equals to your lambda, and that would be 1 over 5. Okay, so I need to show you obviously how you want to do this. So let me see if I can get to my R from this laptop, or iPad, I should say. Did I show you how R works before or no? Don't remember. So, so probably you can see my screen. Here's the R icon, right? Or the shortcut on my desk, on the desktop, I guess. If you click on it, it looks like this. You're more than welcome also to download R Studio. Let me see if I can you guys see the R or no?
I can see.
Yes.
Yes.
Okay, good. All right, so all you need to do is really type in what I showed you, the code. So you want to go P of gamma, and then 12 comma, and then the shape equals to 3. And then the rate is going to be 1/5. And that would give you, oops. I
Oh,
made a
shape is
mistake.
typo.
Yeah, thank you. And that would give you the probability to the left. So in this particular case, it's 0.43 or 43%. So I'm just gonna see if I can copy this and then paste it maybe on the whiteboard, and I hope it works. That is basically the R code. So you're more than welcome, obviously. Nope, it did not work. To use it. Let's try one more time. All right, so here we go. So the probability is going to be this, 43%. So going back to the whiteboard. All right, so that is just the R code. Any questions? Okay, so that's the gamma. Now we are going to move into the gamma Poisson formula. All right, so any questions on the gamma so far?
I'm good.
All right, so let's move on to the gamma Poisson formula. So we would like to make always like a connection between the different distributions. And in this particular case, there's a connection between the gamma and the Poisson. Remember that the Poisson is a discrete distribution. So a lot of times, instead of me working with a gamma, I'd like to, for some reason, work with a Poisson, which is simple to understand and it's discrete. But how do we make that transition? So let's go over that. So computations of gamma probability, which involves integration by parts. Now, of course, nowadays, that's not a problem. You just, you get it from either SAS or R or, your favorite software. Can be significantly simplified by thinking of the gamma variable as the time between some rare events. Remember that time between some rare events, that makes the link to the Poisson. So if you let T to be the distribution of time of alpha's rare event, and X to be the number of rare events that occur before time T. So basically, if you happen to have a gamma random variable, in this particular case is T, then you can define a new random variable. You can call it X, and X will be simply the number of rare events that occur before time T. So we are going to get, we'll get to that. And this T is related to this T. So this is your random variable. You can think of this as some realization T. So if T is this gamma of alpha and lambda, then remember that a Poisson is a single parameter distribution with a lambda. But its lambda here is going to be lambda times this T. Right? Remember, this is like some realization, like some fixed time. Okay, so So going from here to here is basically, let's go over this one more time. You're having some t that is gamma of alpha and lambda. That is established. It's modeling, the total time. Then you can define a new variable. You can call it x and define it as the number of rare events that occur before some time fixed time little t. All right. Once you have that, and you're going to see how this plays out. Once you have that, then your x can be modeled as a Poisson of this lambda times this t. All right, you can see that alpha is not yet, incorporated in the Poisson. Okay, so the first bullet point says that the event t greater than this little t means that the alphath event actually occurs after the moment t, right? So it says that, you remember that t is the total time. All right, this thing is not working now. All right, can you guys see my slides?
No,
Closed on me.
I
All
just see
right,
it.
yeah. Let me pull them back up again. Okay, so let me just get to it. Oh no, it just closed on me for some reason. Okay. All right, here we go. So we were here. Okay, so so pretend that, here's your timeline. Remember that you want to think of this as some fixed t. So when I say, and then this big T is the total time for, the different alphas event, right? So we are saying that the event or T, the time T is actually greater than this little t, means that the alpha's event, so you're saying that it took more time, right, for the whole process to be completed. That means the alpha's process, or the third compilation, when we talked about compiling a program that consists of 3 blocks, that means the third block, right? The total time happened to be after this little t. That's what this means. So, which means obviously that fewer than alpha rare events is going to occur before that little time t. So if I'm thinking of a total of 3, that means less than 3 is going to happen before t, which makes sense. So here is the transition from a gamma to Poisson. If you're looking for the probability that a gamma t time is actually greater than this little t, that is going to translate into the probability that x is strictly less than alpha. You're going to make the flip. You're going to flip the sign. Here you're thinking of this probability as a gamma. Here you're thinking of this probability as this Poisson of lambda times t. So you take this t and multiply it by a lambda. That, of course, is equivalent to this guy. So if you're looking at the complement of the left-hand side, which is less than or equal to t, right? That is the same as a probability of greater than or equal to alpha. And here it's important if you were to include the alpha or not include the alpha. Remember that the inclusion of the endpoint when you're thinking of a discrete distribution is critical. If it's less, if it's less, this is strictly less, this is greater than or equal. So just saying greater than alpha is not the same as greater than or equal to alpha. The left-hand side, it does not matter because T is a continuous distribution. You need to pay close attention when we are looking or working with the right-hand side. That is the probability of the Poisson. Okay, now let's think of how we are going to apply this, right? So what is this useful for? So let's probably try to write this out on the whiteboard first. So I guess let's give me a moment here. So the gamma Poisson formula. So if you have T to be gamma of alpha and lambda, and then X is going to be a Poisson of lambda times T. Now, the probability that T, so I'm just copying simply what's on the slides, of T greater than little t is the same as a probability that X is strictly less than alpha. The probability that T is less than or equal to little t is the probability that X is greater than or equal to alpha. Okay, so so now let's look into an example on how this can be used. So I'm going to copy this example real quick and hopefully I can finish it before the end of class today. Okay, so in this example, we are looking at the compilation program consists of 3 blocks that are processed sequentially one after another. So that's exactly the same example that we did before, right? So you have 3 blocks, 1, 2, 3. The time that it takes to compile each one is exponential with a lambda of what? Of 1/5 because the mean is 5. Okay, so that's just basically the same example that we did. Oh, sorry, 1/5. If I'd like to model the total compilation time, which is t, then t, it was what? Was gamma with an alpha of 3, because I have 3 blocks, and my lambda is just 1/5. Okay, great. So let's look into what comes next. The question is compute the probability for the entire program to be compiled less than 12 minutes. Now I want you to use the gamma Poisson formula. So we just answered the same question by looking at simply the exact area to the left. And we used R to compute that. So the question now is asking to use a Poisson, the gamma Poisson formula. So we're looking for this, right? Now let's see what is needed. So if I need to use the Poisson gamma formula, I'm going to have to introduce a new random variable, which I'm going to call it X. Your X is the Poisson version of T, right? So this is my Poisson. And my lambda here is going to be 1/5. So remember that so here, I just copied this down. It's going to be your lambda times your t. Now remember, what is t coming from? It's coming from the probability question. Now, if I am looking for the probability that t is less than 12, that is your little t. So it's going to be 12, right, times your lambda, which is 1/5. So this turns out simply to be an exponential of lambda with 12/5. Any questions on this? Questions? All right. So now let's try to calculate this using the Poisson. So here are the connection between the gamma and the Poisson. What I'm looking for is a probability that t is less than 12. All right, so I'm kind of like stuck here. What should I use? Can I use this or no? What do you guys think? So what formula should I use? I'm looking for the probability that t is strictly less than 12. So which one should I use? Is it okay to say it's the probability of t less than or equal to 12 or no?
No, it should just be t is strictly less than 12,
Why?
because the question said that what is the probability that it's less than 12? It didn't say equal to 12 also.
Sure, but can you guys tell me, is t a discrete or is it a continuous distribution? What type of a distribution is t? T is gamma. What is that?
Continuous?
Continuous. Does it matter if I include the endpoint or no? Does it matter if I include 12 if I have a continuous distribution?
No.
So it doesn't, right? Basically, you're looking at some picture that looks like this. Imagine that this is a gamma curve, and here is 12. And I'm saying basically that I'm looking at the probability, which is the area of 12, but I'm not including 12. So I'm making it like a dotted line here. If I were to include 12, that means I'm including, whatever that is. So what is the area above the 12 is actually 0. There's no area. So it doesn't matter, right? If I'm looking at a continuous version, it doesn't matter if I were to include 12 or not. So basically, this is the same as saying t is less than or equal to 12, right? Is that clear to everyone? And the reason for that is because t is a continuous distribution. So then I can make the jump to the Poisson using the second, formula, which says it's x is greater than or equal to alpha. So this becomes a probability that x is greater than or equal to alpha, which is 3. Is that clear?
Yes.
Okay, and then all you need to do is, I want to use a calculator for that. So this is just 1 minus the probability that x is less than or equal to 2, or strictly less than 3, right? This guy is the same as this. And in this particular case, you want to use a Poisson of 12 over 5 to figure out this probability. So I'll give you a moment to do that. You want to go to the Poisson CDF on your calculator, right? So under distributions, you should see a Poisson CDF, right? So with a CDF, it's asking you for what is your lambda. Your lambda in this particular case is going to be 12 over 5. Your lower bound is going to be 0, because it's possible that x is 0. And your upper bound is going to be 2, because I'm including 2. Greater than or equal to 3 is the same as 1 minus the probability that x is less than or equal to 2, right? You're not including 3 here. So that would be a 2. So that's going to give you a 0.57, right? So I'll give everyone a moment to try that. And therefore, that gives you a total probability of 0.43, which is very close to what we got when we did it exactly. So you need to you need to be careful when moving from this step to this step. Greater than or equal to 3 is the same as 1 minus less than or equal to 2. And then this is the same because of the fact that t is a continuous distribution, and we make this jump, just simply using the connection between the two. So please, on your formula sheet, make sure that you write these formulas, accurately, just like double and triple check them, because some things like this may show up on your midterm. So any questions on this problem?
I actually have a quick question.
Mhm.
Why
Go
is
ahead.
why is lambda 1/5 and not 5?
Okay, so let's go back to the question. So the reason for that is it says here, each block takes exponential time with mean of 5 minutes. So if I'm saying that the time is exponential, but it's clearly states that the time x is exponential, but the mean of time, which is the expected value of your time, is 5. That doesn't say that lambda is 5. It says that the expected value of x is 5, or the expectation of the time is 5. Well, we do know that if x is exponential, then the expected value is 1 over lambda. So if you solve for lambda, your lambda is 1/5, is not 5.
Okay, thank you. That makes sense.
Makes sense? So when you read the problem, that's always like students make a mistake here. Once you make this mistake, everything else is wrong, because you'll be using a lambda of 5. The probability will be wrong, like everything, because everything is interconnected. Any other questions? All right, everyone. Thanks for joining today's session. And before you guys leave, let me just make sure that I got everyone here who I did not in terms of attendance. So is Muzahidul in today? Michael C.
Professor, I'm right here.
Muzahidul,
Mike-
okay, good.
Michael
Michael-
C's here.
Okay, thank you. And Sahil, is Sahil in? Sahil? Christopher Lynch? Chris?
Yeah, I'm here.
Okay, thank you. And then Brian R.A. Ron?
I'm here.
Oh, thanks. Alexander Rotella? Alex?
Here.
And then is Jimmy here? Jimmy?
Here.
Okay, thank you. And then John Ward. Is John Ward in?
I'm here.
Oh, awesome. So almost everyone is here today. All right, thanks everyone for your attention, and I'll see you next.
Have a good weekend.
Have a good weekend.
Yeah, you too. Have a good